So we're back at the 1,100-foot Supertower in St. Louis, and you guys had a lot of questions last time. For instance, this is a megawatt tower, but what does that actually mean? There's a lot of comments about ERP and things like that, so we're going to get to all those questions and explore this tower in a bit more detail and talk about some of the cool things that we missed in the last video. Here on the Gearling Engineering channel with Joe, and I'm Jeff, his son. And let's get started. So after the last video, a lot of people were talking about how this tower, it's not actually 1,000,000 watts because the power that goes up is like 300 kilowatts, a little more than that. And you were talking about antenna gain factor and things like that. So is it clickbait to say that this is a 1,000,000 watt tower? What does that mean? A lot of people were mentioning something called ERP.
Yeah, so ERP, effective radiated power, it's a good way to think about that is it's receiver oriented. So if you have a receiver in the field, and you have a standard no gain antenna with so many watts in it, what will the receiver see? And if you have a multi-bayed antenna system, the RF that radiates out is more intense, so you get more coverage. You get a denser signal out to the area. The equivalent power to do a single bay, you would have to literally run megawatts, say up a tower like this, to a single bay that could handle it. It would be a huge amount of metal and stuff involved. And so that's impractical. So the ability to cover an area with an antenna system that's reasonable to build and make, that's how you have to think about it. So yeah, the radiated power is equivalent to 1 megawatt, but the actual RF energy piped up would be less.
You're standing here at the base of the tower. A lot of people had questions about safety and RF. And at the front entrance of this place, there's also signs about people that come on site need to have proper training in RF safety. When we were inside, we saw how thick some of those cables were with hundreds of thousands of watts of RF energy. And I'm imagining there's many hundreds of thousands of watts right here. Why aren't we dying right now?
The big thing about the biggest antennas here is that the energy is carrying up inside on the center conductor all the way to the antenna at the top. So your near field exposure to that kind of energy is blocked by the outer conductor, you know, the coax cable.
So you're saying that way up on the top of the tower, way up there, that's where the RF energy is coming out mostly. And there might be a little bit of loss through here, but it's not like down here, it's
yeah, you're safe. Yeah, down here is a safe place. And there's a whole set of ever-growing knowledge base added rules that the FCC and other agencies of the government require you to follow. Tower crews, by the way, almost always now wear a device that monitors for high RF levels. When we say radiation, it's like light bulbs radiate, the sun radiates. So when we say radiation of RF, it's a very low frequency compared to like X-rays and nuclear stuff that you're worried about. So you're talking about a thing where it's more about heating tissues than it is about getting some kind of cancers and things like that. There's just no evidence that I've ever seen collected that says that frequencies like we use on this tower would cause those kind of things.
Yeah, and down here at the base, we're so far away from the actual radiating antennas.
Yes.
that energy is going outward,
yeah,
not downward. So
yeah, the antenna is meant to go outward, and in fact, a lot of antennas, you can take that beam and you can collapse it if you wanted to, or widen it. And of course, a one-bay antenna has the most energy that going out in a lobe form that would spread it up high and low, which people hate to send energy up high because it doesn't do you much good, and especially in FM.
Unless you're in an airplane.
Unless you're in an airplane and want to receive the station. But then you're receiving like 400 stations on that frequency, so not such a good experience.
But it's a little bit ironic that we're in the middle of a cemetery.
It is ironic. Nobody has ever complained about near field radiation here, that's for sure.
In the building, we saw those giant coax lines. You can see that there's some that are hard 90s up here and other ones that seem to be like bends, gradual bends. How does this all go up into the tower in a way, especially those rigid connections I see up there? How do we make it so that if the tower does move a little bit, that those connections don't break? Or is that actually a problem that you have to deal with?
The copper rigid line, I mean, that stuff is like, it's copper piping, and it's hard, and it uses elbows to turn up the tower, and you have to hang it. So it expands and contracts. So you have to have a system that allows that movement for expansion and contraction at every connection. They have hangers that have flexing in the hangers that hold those things up. You can imagine the vertical weight of a 6-inch copper pipe with a center conductor in it, And you could just imagine the weight of that wanting to fall down and having to hold it up. On the grounding, on these cables, you'll slice the outer protective coating, and then you'll clamp around it the grounding kit, and then it'll have a braided wire or something coming off of it that will look for the ground. That'll clamp to a tower leg, or and you got to scrape the leg to get to the metal of the leg, and then you wrap it all for weather when you're done.
We did have a drone shot of this tower in the last video, and a lot of people were asking, like, how can you get a drone shot? Why didn't the drone either A, catch on fire and fall out of the sky, or B, how can you remote control a drone with all that RF energy?
Like every one of the viewers who asked, it's like, what's going to happen? That was me too. I found I have more trouble in front of 5G and 4G antennas from cellular than I do with the radio, but that'd be on the drone manufacturer, the frequencies that are being used to communicate with the drone. If they're free and clear of any cross compatibility, it's only the heavy amount of RF. So staying back away from the antenna. Most tower sites, you want to check with the owner and make sure they're cool that with your level of drone expertise, and that they don't have a rule that says no drones, no flying a drone on our properties. The drone is great. You can inspect the tower, you can inspect somebody's work and see the antenna installation pretty quickly with a drone. So if I wanted to check the guy wires 5 or 6 times a year, I can do a few of those at least by just flying it. You can fly up and see missing bolts and hardware that's loose, or tape that's coming off of a weatherproofing kit. So it's a great inspection tool for guys like me that would not be climbing.
So there's a satellite dish here with a cover over it. I noticed a lot of these don't have covers. And I also saw over on some of the generators over there are these covers.
Those are ice shields. And if you could imagine, you know, getting a ½ inch or so of ice here, which in St. Louis is rare, as it starts to melt, any kind of thing that causes it to chunk down, especially like the guy wires, you have ice all over the guy wires. As that starts to melt and move, that ice will fall. They just float and move to different places within proximity of the tower, but not just down straight from the towers.
It's kind of like a risk mitigation thing. It may or may not ever hit your dish, but if it does, that'll protect it. If it doesn't, you're lucky. And because I noticed some of those generators, a couple of them have the ice protection, a couple of them don't.
So you've got a generator engine and a generator plant inside of a box that has a gap with a metal roof. So ice hitting it would probably put a nice dent in it, but it wouldn't break it. Whereas a dish like this, if it gets hit with ice, you've totally changed the dish, maybe the angle, but you've definitely changed the dish's curve to hit that receive point.
Some people are saying, oh, you're not wearing your hard hats. Is a site like this, is a hard hat really required, or is that?
Well, if there was work on the tower, we would be wearing hard hats, or we wouldn't even be on the site. You know, there's a level of acceptable risk, and if the guys were up there, especially if they're mounting antennas and bolts in their hands, it's like, I've even dropped a computer once. But you can drop bolts pretty easy, and they do the same thing, and a 300-foot bolt drop from a tower is not good for your head.
They always say, like, lightning is going to hit the tallest object in the sky, and that tower's pretty darn tall. Is that something that happens regularly here? We have a lot of storms that roll through St. Louis.
Towers get hit with lightning a lot. At the top of the tower, you'll often see some sort of a spiky, wiry thing. That's to attract the static before the charge builds up so much that it becomes more of a problem. They've discovered through studies and with modern equipment, towers create a bubble of lightning protection that go out farther than you would think.
So everybody should be asking for a tower in their neighborhood.
You would want a tower in your neighborhood for sure.
Except for the falling ice, which would kill you.
Yeah, watch out for the falling ice, which would allow you to have a super strong roof structure, which is also good.
And you'd have to wear a hard hat every time you play in the backyard.
When you're cutting your grass in a hard hat, that's good too.
A number of people mentioned that you were holding this old-fashioned incandescent light bulb, and why doesn't this tower have LED lighting? This tower was built in the 80s, so LED lighting was not there back then.
Not a thing.
Is it a thing nowadays, and is it?
It is a thing. There's a lot of towers using it, and it really has to do with, like anything else, like at what point in time does it make sense to invest in the LED lights. And when they first came out, there were a lot of failures going on in the LED world. We all probably experienced them with our home lighting and so forth. So the technology's gotten really good. So now it is just a matter of financing it, you know, over what it costs to pay and light these and change them versus an LED. During events, you know, you could lose an LED light, and then you're changing a very expensive enclosure where these, literally, you've got a standard little socket that usually doesn't fail and a bulb that does fail after so many years. That's a pretty thick filament going across there, so they are meant to last a while.
And there's also this giant flasher looking thing.
Yeah, so this, like a lot of them used to stand here and you would hear zzz, click. You'd hear the mechanism in there rotating around when I started. They literally had a motor turning an arm, and the arm would slap a closure and turn on the light.
A lot of people were wondering with these giant, huge tubes, a lot of people were calling them waveguides, but you said they were coax. Can you tell me what the difference between a waveguide and a coax is?
A coax is, it's literally their center conductor and the outer conductor are on the same axis, right? So you get coax. And waveguide, it may be the same, except the waveguide shape is determined by the frequency of the energy. It travels differently at super high frequencies compared to what it does at our frequencies, which may seem high to some people, but they're actually lower frequencies.
How do you do a 90-degree without that thing cooking and blowing up?
Yeah, so you can see what this is made. It's literally what you would expect of a physically made 90-degree, but going through the middle, trying to maintain that 50 ohm center line thing, they put these in the middle. So you can see that at a flat side, kind of see down the middle. And these literally go in there. So you go through and you can see that's going to center up because it's going to mate to one of our bullets. It's going to mate and center with the Teflon, is going to hold it in place. And it's literally going to hold right in the middle. You come around the other side and hold in the middle. Every single connection point has a loss, insertion loss. And as they get bigger, it's more important when you have bigger facilities like this to accommodate all of those elbows. You are engineering this to make sure that if you tell a customer they put in 20,000 watts there and it's going to come all the way through the system and be the right power to get their coverage, you need an engineering guy to know whether that transmitter needs to be at 20 or 25 or 30,000 watts by the time you go through all the losses in the system. So coax, you can see if you look down the line, you're going to see the center conductor and the outer conductor are on the same axis. So you got coax.
So and coaxial.
Yeah, same thing here. You've got a center conductor, outer conductor, same axis, coax. So on your small wires, you've literally got, you can see this is braided. There's a lot of braid there. There's guys that, you ham guys could make an antenna out of this because you know you could have your ground plane and snip that to whatever frequency. So you got your coax here. Outer conductor is actually this braid, and the inner conductor is whatever size wire is in there. And again, this is also deterministic of the frequency range you're doing, the distance between the center conductor and the outer conductor.
So you mentioned down the line one time that there was an engineer that came down that staircase, walked around the corner, and somewhere around here.
Yes, he saw an elbow, one of these elbows in this area of the previous system, it was replaced since then, was flaring out this blue fire and scared the heck out of him. It makes a weird noise, it smells different, and it's not probably good to be around very long. But that happened here, and again, that was caused by an accident where the guy pumped in too much of the oxygen at a time, and it was cold. The air's cold, it condensed inside, blew an arc. Safety systems are there to prevent that from going on so long that it would, say, melt down a site.
Why not just have an antenna for each station and not have to have all this combiner stuff happening?
Well, the issue, if you look at a facility like this, is you've got land and then you've got your vertical real estate. If every station had their own antenna and they were all 8 bays and you had to have 10 feet between the bays, you're going to have 70 feet for an antenna, then you're going to skip a little gap, 70 feet for an antenna, skip a gap. So they have 10 antennas. One of the antennas is going to be barely off the ground. So the idea is you put less on the tower and do more work on the ground because you have plenty of ground around the base of the tower. But it's better for the signal to be at the highest possible point, in this case with the most optimized rounded signal in the center of the population, the Supertower.
There's this cooling unit on top of this combiner, and then over here we got a little desk fan. Yes. So what's your opinion on these little engineering solutions?
What they're doing is cooling this super magnetized box here that is allowing us to inject HD carriers for the digital audio system we use in America. But it combines to this box, and we found at this site these boxes get kind of warm, and as the metal warms up, you know it changes. Critical wavelength oriented metal changing is not good. So people one by one started figuring out they need cooling. So you have a low engineered version, a high engineered version, and a medium engineered version.
Just got a couple computer fans.
That's right.
Nice.
This transmitter, they're all solid state now. So you look in and you're gonna see a whole bunch of power supplies servicing a whole bunch of RF modules. There's a mixing, the RF gets mixed in the back and goes out the top. And then this is the controller board and remote control. You can hardwire to the remote control unit to close switches, but you can see you can get the data on every device in there. Your exciter, which you guys that use exciters will know what I'm talking about.
What is an exciter?
An exciter is like the starting point for the creation of the RF signal. So you're going to send audio and other information into it, and it's going to create the modulated signal that gets amplified.
You mentioned in the last video that the HD, the coax coming out of it is a lot smaller. Does HD have less coverage than analog?
No, it's the nature of the digital carriers. As we know, it's easier to see something is on or off than it is to see hundreds of levels between. So you're talking about digital, you got a bunch of individual carriers going on and off, so it's easier to detect and decode and get data out of that. And so the coverage is good, even though the amount of RF is smaller.
From the other transmitter, you see that the middle has all this stuff going up and down. That's the frequency modulation. Yeah. But here it's just digital. It's just ones and zeros on either side.
Yeah. So if you did digital only, you could fill this in too, right? So now you got more data that you can send to a receiver to have more audio channels, more data, video, whatever else could be carried. But you're literally reserving this space because it has to be analog, so you can still receive the old analog signal.
Some people are commenting that in Europe there's DAB+. Yeah. And do they even have analog FM anymore?
They wouldn't need it. So when you convert to the DAB, what they did is they took a higher group of frequencies, and it's more like a cell site system where they have a lot of transmitters around the city that all transmit your frequency within a band, and your digital tuner, which has to be a new car tuner, would tune in and receive whatever channel is on that band. And as you travel, you can go, as you travel, it transitions from one channel to another, just like your Wi-Fi would if you're walking around with a car.
Those don't look like they fit in this guy.
No, these are outdated. They're tubes. Probably make a great audio amplifier. Not really, but you can see the tubes, all the connection points to heat the filament. You got the fins where we'd blow the air through to keep it from melting down. AM stations don't have tubes, but they can be, like KMOX, 50,000 watts in St. Louis. That's a lot. I mean, it's a transmitter a little bigger than this, does 50,000 RF watts, and it sends it to the tower. And the tower is hot. Do not touch. RF burns, and if you get an RF arc into your bone or something like that, I mean, it's burning all the way through. It's not a surface burn like it is with fire. It's not cool. Avoid RF burns.
Can you explain what reflected kilowatts means? And I see there's like a little red line there.
So this is real old school. You can see it's got the Y2K sticker. It is literally in line, in that 3-inch line. You put in sensors that are looking for forward power going out and reflected power coming back. And of course, you would love everything to go out and nothing to come back, but that's not reality. So you can see the forward power here and the reflected power here. You want to see motion. So you should have a normal place for the forward, a normal place for the reflected. This red line on the back of this, if that shoots up, hits that red marker, which you can adjust in the front here, it will trigger an output that can shut down your transmitter. So that's to protect your transmitter from getting so much energy back that it would blow a tube or RF section.
There were a lot of people who are ham operators, amateur radio and all that, who were quite impressed. They were very impressed by the size of everything in comparison to probably the setups that they have. But a lot of people asked, are you a ham operator?
I am not a ham operator, but I love and appreciate ham operators. Some of my greatest mentors were ham operators, like Chris Hudak and others. But I do, the ham people are special. They go from really amateur techie get people to super understanding RF geniuses who've played a million different scenarios for antennas and wire and stringing across from trees to homes. And it's an amazing story. So I love the amps.
That was a lot of the questions that we heard. If you have any other questions, please comment below and we'll try to answer those in some follow-up videos. But hopefully, I'm having surgery soon. You might not see this video until after I've had the surgery, but hopefully next year we'll head out to an AM tower, which
definitely.
you said is a lot different.
They're a lot different.
Actually, the tower itself, things like insulation and how the tower works and how the signal comes out. Maybe we'll also do a TV station, some other things. So please leave your comments below with any questions you have that you want to get answered, and we'll see you next year.
So long.